Hi everyone, welcome to this M2D2 meeting. Um, our speaker today is Yanis Von. He's a research scientist at IBM Research in Zurich. We have a focus on scientific language modeling, and between 2019 and 2022, he got his PhD jointly from the IBM Research Unit and also the MN Computational Biology Lab at UTH Zurich. Thank you so much, Yanis, for accepting to present your work with this group here today, um, and looking forward to it.
Okay, so hi everybody. Thanks a lot for the super nice introduction. So good morning, good evening, good afternoon, wherever you are. And yeah, I'm very honored today to be here to speak to you about our recent work in generative language models for molecular discovery. I'll be covering some of our recent publications, including the Regression Transformer, GT4SD, and some others. And yeah, if at any point of the talk you have a question, just feel free to interrupt. You can just raise the hand, and then I should see it, and then can give you the mic basically. Okay, cool. So let's get started. I'm sure you've all seen this, the design, make, test, analyze cycle. This is really at the foundation of molecular discovery. And our success in accelerating this cycle will be pivotal to combat global challenges such as the climate crisis or emerging diseases. And there are several bottlenecks with this cycle. One is in the costly and slow make step for the chemical synthesis, right? But the second bottleneck is also in the design step, where hypotheses are often proposed by humans in quite ad hoc manner. This is done because the search space is practically infinitely large, and as a result, the attrition rate is extremely high. So only 1 out of roughly 10,000 synthesized and tested molecules make it all the way to the market in drug discovery, for example, and even if it takes 10 years. So we have to make sure to improve the quality of the average hypothesis that we evaluate in the lab. And to do that, we can think of an additional small validation loop that is embedded into the real discovery cycle. And we call this the accelerated molecular discovery cycle. And if we're thinking about molecular generative models, we should identify like a couple of challenges that I think will be important to address. One of them is flexibility. So we're always looking for flexibility at inference time. We would like to have models that are not too task specific. For example, these days it's quite easy to develop a generative model that can propose molecules with a high log p value. But then, for example, if you were to interested in generating a low log p value, you might have to retrain your model. We really aiming for flexibility at inference time. The methods should also be or facilitate local search, because oftentimes in material drug design, you do have a good initial guess already, right? And you just want to sort of like refine and locally adapt your molecules. And third, maybe a bit less popular, but in my view is also really important, that we develop methods that bridge property prediction and molecular generation. And why that? So essentially the conventional approach would be to maybe have a predictive model and then develop it completely separately from a conditional generative model. So it might look like in the scheme here on the right. These two things, they are never, in almost no existing work, they are jointly parameterized. They are almost always independently parameterized. And this to me is something that is very unintuitive. And I would raise the question on, when we're trying to understand molecules, whether we can actually model structure without modeling function. So to draw an analogy, if you think of an astronomer and the job of the astronomer is the generative model in the analogy, the astronomer has to design a new telescope. And the astronomer has no clue about magnification. And we all know magnification is important for designing telescopes. Then I think this astronomer will have a very hard time in like creating and designing a new telescope, right? So it seems that especially in molecular discovery, like structure and function are really closely related, and therefore it's very obvious that we need models that can also do both of these concurrently. So we will propose a model that can do that, hopefully. And how are we going to do that? Well, it doesn't come as a surprise. These days, we will use transformers. So why are transformers so successful? Across many domains like NLP, but also computer vision. We've seen vision transformers. They've been impacting computational chemistry, computational biology. So one of the reasons it's so successful is that it's really sort of the intermediate convergence point of a steady decline of inductive biases we've seen. So when deep learning rose to power like 10 years ago, we saw CNNs replacing handcrafted feature detection methods. A few years later, we got to see self-attention, which essentially generalizes fully connected layers because it applies sample-dependent instead of static affine transformations. And now with transformers, which are so universally useful that even entire problem domains like offline reinforcement learning are basically being reformulated as sequence modeling tasks. This is what we saw in the decision transformer paper, right? The model we are proposing, we dub it regression transformer. And one of the main ideas here is to extend masked language modeling to also include numbers. And this is achieved by representing numbers as token sequences. So it's a very intuitive approach in a way. But so up to this point, if you were to solve a regression task with a transformer model, you needed a task-specific regression head, right? And this also implied that there was sort of like no way to do self-supervised pre-training on numerically labeled data sets. But our approach with this model is to construct these sequences that can contain, basically in the first place, they contain a chemical entity, given here in the form of a SMILES. They also can contain an arbitrary number of property names. Here it's a QED, so drug likeness, and a toxicity score. And then they contain the property values, which are simple floats. And then the last thing, okay, the separator tokens, they are the only meta tokens we have in the vocabulary. Now, we're tokenizing the sequences. Basically, we tokenize these property values on a character level, but there's one twist. We essentially keep track of the decimal order to differentiate the position of each token. So for example, you have the 5 token here, it has a -1 here to basically denote that it's at the first position after the dot. So, okay, I'm going over the details of this paper now. The paper actually got published like, I think around 2 months ago in Nature Machine Intelligence, should have mentioned that. So essentially, when you're using masked language modeling on these queries, you can abstract regression as a conditional sequence modeling problem. So, and you can see an example of this here. You have a sequence here. It's sol is the property name for solubility. You have a few tokens that are masked, and then you have the SMILE string. And if you let the regression transformer fill these masked tokens, you get a sequence of characters that then you can sort of map back to hopefully a valid floating point number. Now, why are we doing this? So the beauty of that approach is really that you can also just at inference time change the position of the masked tokens, and then you get a model that can locally adapt that can basically locally adapt molecules in a property-driven manner. So you can see an example here at the bottom where you have a few masked tokens in the molecule, and at the same time you can plug in a desired solubility value. You can then decode with the same model, right? And you will obtain a molecule that then hopefully will adhere to the property constraint. So this is really a sort of like dichotomous model that can seamlessly transition between predicting continuous properties and property-driven text generation. And in a way, it's relaxing the inductive bias of discriminative modeling, where we learn joint distribution, and instead it's sort of like learning joint distribution over input and target variables. So we are bridging both worlds here by concurrently modeling structure and function, I would say. So it's a very flexible model, as you can see, because you can start the generation from a scaffold or completely from scratch just by providing the property value, or you can just mask one token, so one atom at a time. And obviously, it's also a very local search method. All right, so okay, I already see a question in the chat about the loss. So okay, yeah, I will get to the loss in a second. So the application domains for this approach are very diverse. So we'll show applications on small molecules, on proteins, and also on chemical reactions. In principle, you can also try it on natural text. It's a bit less likely that you find examples where numerical properties are so closely linked to a text snippet in natural text. So it's something that seems to be more prevalent in scientific languages like SMILES or amino acid sequences. So we have to talk about the backbone we are using. So there's a whole zoo of transformer models, and it's a critical question which backbone we pick. The requirement we have for the backbone is that we want to be able to predict multiple discontiguous mask locations while having access to the full remaining sequence. So you see an example here. We have sequences like these where the property values are masked and the SMILE string is at the end. So now clearly, if we would use an autoregressive language model like GPT style, this would not work, right? Because it's left to right sequential. So once you hit the first mask token, you don't have access to the SMILEs. We know Baird-based models, they are nice because they have like full bidirectional attention. And they were super successful for self-supervised pre-training. But the problem is that BERT basically factorizes the joint conditional probability with an independence assumption. And this means that all mask tokens are predicted independently from another. And this is why BERT really sucks if you really want to generate longer snippets of text. And yeah, you clearly in this example, you don't want to fill these mask tokens independently from another because yeah, I think it should be obvious because the value that goes in the first slot will like govern a lot what goes to the second slot, right? So therefore we use XLNet. XLNet relies on permutation language modeling, which combines the benefits of autoregressive models and Baird-based models. And the main twist of XLNet is that we, as you can see here, it is sort of like sampling the factorization order at runtime, but it's sampling in such a way that it is guaranteed that the mask tokens are in the end. So in a way, you're sort of like, you are passing through the sequence left to right, but in a random manner, you still have the positional encodings that are actually telling the model what is the correct order. And then you just have the mask tokens in the end. This is what's happening under the hood. And in expectation, this gives you an autoregressive model that has full bidirectional context. Now, as a note, in theory, you can use any other backbone that facilitates to fill multiple discontiguous mask locations. There are some out there, MPNet is one, or also you can use a T5 that is using this trick with a Sentinel token, right, to reformulate things in a bit of a question answering scheme. So now the objective we are using for the model, the vanilla one, this was for the first types of experiments we did, is really just the XLNet objective, which means we randomly mask 20% of the tokens and we're letting the model predict those ones. That's it. We make no distinction as to whether a token belongs to the chemical or to the property. So with that, let's jump to the first results here. Really, our hypothesis or our goal was to verify whether we can learn regression purely based on token sequences. You can see the property prediction queries here at the top, right? We just fill these green mask tokens. And the first thing we noticed was the model always predicted a sequence that maps to a float. And actually, it understands this synthetic property relatively well. So if we compute the Pearson correlation, so PCC will always be Pearson correlation today, then we have a PCC of around 0.97 between real and predicted QEDs. We initially started with SMILES, but then we later switched to selfies, and all the other experiments I'm showing rely on selfies because selfies are easier to handle for generative tasks. We are also, as you can see here in the plot that in the table at the bottom, we are outperforming like simple K and N baselines. This is, I think, already is interesting because the thing you have to realize is, I mean, this model solely relies on a cross-entropy loss. This is nominal scale loss. We are not having a ratio scale loss like in a mean squared error loss. So there's no proximity of numbers. If the correct answer is a QED of 0.95 and you say 0.96, it's as good as saying 0.05, for example, right? The other thing I want to emphasize is that this is sort of a few shot setting because these queries that we are evaluating, they always look like the one shown at the top. But at training time, we don't make any assumption about where we put the masks, so we randomly put them anywhere, right? So yeah, it's not really what we're training And we will improve on that in a second. Now, one thing you might wonder is, okay, I mean, you have to learn embeddings now for all these tokens that are just representing numbers. And actually, we know the proximity of numbers to another, right? So why shouldn't we have an inductive bias for that? And we did that. So we invented these numerical embeddings, which are very similar to positional encodings. They are, in the first place, they are zero vectors for all tokens, but for the numerical tokens. You can see an example here in the middle, and they're governed by this equation that is shown on the left. And essentially, you have, you have these values that are just these embeddings that are just designed essentially to preserve similarity of numbers. So if you, as you can see on the right here, if you plot the pairwise distances of all numerical encodings, you will see that they preserve similarity of numbers. And then these embeddings, they are added to the learned embeddings, similar to positional encodings. Now, does it help? Well, surprisingly, almost not at all. There's a slight improvement. I see a raised hand. Yeah, please go.
Yes, sorry, is about the previous slide. Were you learning the embeddings like at the same time as the rest of the network? I mean, using this new loss to kind of learn that, or was it
Yes.
kind of pre-trained somehow? Like...
No, so it's a good point. I should comment on that. So we took the XLNet backbone, but we trained it from scratch on molecules. We didn't initialize it with like pre-trained weights on natural language or so. We had these extra tokens being added to the vocabulary, to the vocab for the numbers, but they were treated just as the normal token in the smiles, and they were just learned from scratch. The model has around 100 million parameters, and we trained this single GPU, but for a couple of days, because permutation language modeling is really slow to train. That's one of the drawbacks, because you have to sample all these factorization orders at runtime, and yeah, it's a form of data augmentation that is a bit implicit, but it just makes the model really slow to train. Yeah. Does it answer the question?
Yes, perfect. Thank you.
Okay, cool. Yeah, so as I was saying, so it doesn't really help improving the model. I mean, to a slight extent it does. If you compare the numbers of the last row here, you will see they're slightly better, but not really much. And we wanted to understand why. So, and the reason is that the model learns the proximity of numbers in the absence of these numerical embeddings, but only in the absence. So if you provide them, the model doesn't have to learn it. But if you don't provide them, you can get plots like this one here, where you see on the x-axis the digits from 0 to 9. And on the y-axis, you see the embedding value. And clearly, you see that the model is just ranking the numbers, right? And this is just not, it's just not this cherry-picked example. We see this is happening for almost 50% of the dimensions. You can see this on the right. So wherever you have like a color gradient from left to right, it's essentially a ranking dimension. And yeah, the significance of the statistical test here is indicated by the stars. So this is sort of like surprising, because there was no explicit supervision on that, but the model figured out by itself that, I don't know, a 7 is in between of a 6 and an 8, for example, right? Okay, so, but after we reassured that the model has good representations of numerical properties, we wanted to test it on molecular generation tasks. And we can see an example on this here. So this is achieved by simply masking now on the molecule. So another part of the sequence, we never mask on the property in this case. Now, what do we do and how do we measure performance? So we perform 10 decodings, and we each time provide a different property primer. And these property primer, they are our desired, the goal, the property the model should produce. And these primers are spaced equidistantly between 0 and 1 in the case of QED, because QED goes from 0 to 1. And you can see here in the green color plot, all the unique decodings. They are ordered from low to high QED primer. The seed molecule is shown in the middle. And you will see that in general, the higher the primer is, the higher is also the QED of the generated molecule. Now, the performance metric we're always reporting is the Spearman rank correlation between these primers and the generated, the QEDs of the generated molecules. And for the Celsius model is around 0.47. So we can see, I think, and appreciate that the regression transformer learned to decorate seed molecules based on continuous property constraints to some extent. Now, let's look into the objectives again, because again, the evaluation queries we've had here, right? They were just a really small subset of all the training queries the model was exposed to. And we wanted to come up with an improved training scheme that can essentially allow us to maximally, or to be as good as possible at both task, property prediction, and conditional generation. And for that, we came up with an alternated training scheme. So we have two loss functions, and every 50 steps or so, we switch the two loss functions. Now, for the property prediction, the loss function is very, very obvious. We just always mask the property value. We don't mask the rest. So it's a deterministic loss, masking at this point. For the text generation objective, well, the initial and the sort of naive one is this one, where we never mask on the property values, but we always mask on the SMILE string, and we do that randomly with like 20% of the tokens or so. And then we refine this approach, coming up with a self-consistency objective, which essentially really helps the model to become better at the molecular generation. So what do we do here? We, as a first step, use this text generation objective. So first we essentially let the model predict a new molecule given the property constraint. And then in the second step, we take this just predicted molecule and we provide it to the model itself, because now we know that the model is dichotomous, right? It can also do property prediction. So what we do is in the second step, we don't mask on the molecule, but we do mask the property value. And then we predict this property value, and then we compute the loss between this predicted property value and the property value of the seed. And then we have these two loss terms, and then we can sort of like add them together with an alpha parameter to compromise a bit their weight. So if we do this improved scheme, then we basically arrive at the we conclude the methods part at this point of the talk. So we can then have a look at the backbone. So we have these mixed sequences at the top. We tokenize, preserving the decimal order. We have the numerical embeddings that are added to the regular word embeddings. We use the XNet backbone with the language model head. And then we have these training objectives as discussed. Here are some results for this alternated training scheme. So we can realize that it helps the model in both tasks actually to improve performance, this alternated training scheme. What's curious to notice that the alternate training scheme is better than training individually on either task. So in general, we did this pre-training using just vanilla computational language modeling, and then we did in fine-tuning with this alternated scheme. And here in these two rows where my mouse is now, where we have only predict and generate tasks, we see that the model can, in this case, only solve one of the two tasks, right? Because it wasn't trained on the other one. But even these numbers, they are below what we can see here at the bottom, what we achieve with the PLM pre-training and then the alternated refinement. And this shows that the benefits of self-supervised pre-training, they can extend to numerically labeled data. Okay, I see a question in the chat. When training via permutation language modeling in the first phase, are the tokens representing the property tokens masked as well? They are masked sometimes, right? But not always. So it's completely stochastic. We make no distinction. They might be, in 20% of the cases, they will be. Yeah, so sometimes the model is doing a property prediction, but not always. And there's a second question. Do you have any experiments in multitask property settings? Yes, but not in the paper. I will show them in the second paper later, actually. Yes, there's something. And okay, I see the first question was actually about property names. Yeah, the property names can also be masked. The separator token can also be masked. Really, everything can be masked. Okay. So yeah, we see here that in one configuration, we are better in the predictive task, right? If we do the PLM pre-training and then just let the model predict, we are slightly better in the prediction task. We get to a PCC of 0.99. But then if we look at the generation task, the model really sucks, right? And we wanted to have a model that can do both. So this is why the configuration at the bottom is our preferred one. This is the best one. Okay, so this was synthetic data. So then we decided to benchmark the model on a property against classical existing property prediction models. For that, we used MoleculeNet. So I apologize for that because MoleculeNet, I think, has been benchmarked to death by now. But at least it's real data. So we can see that we can beat machine learning baselines like XGBoost, Random Forest. We can outperform them. And this is already interesting because they use a regression objective, right? We just use a cross-entropy objective. We are falling a bit behind to transformer-based models that then have a regression hat on top of it. That is sort of expected. But actually, I have to say that in small molecule property prediction, this gap is bigger than the gap for chemical reactions and proteins, as you will see later. They were basically on par with existing methods. So we are like more or less, I would say, competitive. Then we also always have to realize, okay, the same model now can also do conditional molecular generation, right? So if we just train on a MoleculeNet data set, we can we can also generate molecules that have a desired solubility value, as you can see here. Again, we achieve a rank correlation that is between 0.4 and 0.5 on these two solubility data sets. As you can see here on the lipophilicity, the Spearman rank correlation is a bit lower, more like 0.2 something. And this is because these molecules were relatively large, so more than 50 atoms. And we observed in general a decline in the generation performance when the molecules got really large. And this is probably because the contribution of every individual atom to the property value is lower. Yeah. Okay, so with that, I would like to jump to the next experiment where we wanted to benchmark the model against existing molecular generative models, right? Because we saw benchmarking against property predictors. Okay, now we see benchmarking against generative models. Here we take this task from the junction tree VIE paper from a few years ago, where the goal is to improve the log P of a molecule. So we're given given a molecule and we have to improve its log P, but we have to respect the similarity constraint to the seed molecule. So we can only adapt it a little bit, basically. And here we can see that the regression transformer is performing better than the junction tree VIE and also better than the GCPN, so graph convolutional policy network in both cases. So this is already, I would say, interesting because both these models, they are using gradient optimization schemes at inference time, whereas our model wasn't even trained on generating molecules with higher log P, right? You could equally pass queries and ask for lower log P. We are more or less on par with this MoFlow model, which was at KDD last year, and we're falling a bit behind of this back translation model. But I don't trust these numbers of the BT model too much because they're not really apple to apple, and they don't report the standard deviations of the performances and so. So in general, we get sort of like satisfying performance on this task. Yeah, we can use this approach in different schemes. So for example, on different domains, for example, protein sequences. This is more of a detour to verify the generality of our method. We can see we took here benchmark datasets from tape, and we find here on the left side in the property and the protein regression tasks, we find that we can actually match or outperform state-of-the-art models, including the models from tape, including UniRep and Protein Beat. And at the same time, we can then also do generation, and we can sort of adapt the protein sequences to some extent such that their predicted property value adheres to the property constraint. So I emphasize here in the sentence the locality. So the model is really a local generative model. It does not work well for full sequence generation. It works well if you have a seed sequence and you just want to adapt it like, I don't know, up to 50, 60%, but not entire like de novo design from scratch. Basically, it doesn't work well for that. So with that, I jump to the last application domain, which is chemical reactions. I think by now we're familiar with the concept, so I can go a bit quicker. Here we have data sets of reaction yields. where in one case we just have Suzuki couplings, in the other one we have Buchwald-Hartwig aminations. And also here we can see that we are performing on par with state-of-the-art models like YieldBERT. In this case, yes, a transformer model with a fine-tuned regression head on top. And we are like, having about the same performance. Now for the generative task on chemical reactions, we pick two use cases. The first one is on filling or reconstructing missing data. So these reactions, let's look at these Suzuki couplings. They always contain one electrophile, one nucleophile, one ligand base, and solvent. And sometimes there's missing data. So here the use case we had was like we provided the entire reaction, including the yield, apart from one of the precursors. And then we were trying to reconstruct the precursor. And this worked in most cases. So you see the values are above 50% in everywhere, apart from these additives in the Buchwald-Hartwig actually, but okay. And this can be helpful to sort of like, reconstruct missing data. The second task we looked at is decoration. So here we wanted to design a new reaction with higher yield. And we can see a success rate also that is higher than 50% in almost all the cases, with an average improvement in the predicted reaction yield between 5 and 10%. So an example of this you can see here, there's a seed reaction at the top. We can see the yield is very low, only 5%. And then each of these lines is sort of like one inference query to the model where we replace exactly one precursor at a time. And we can see that in each of these cases, we arrive at a reaction that has a higher predicted yield. And this was, this yield now was not experimentally verified, but just predicted by our model. But then we also were seeking for external validation, and we at least used another model, basically the molecular transformer from RxM. Okay, so take-home messages from this paper is that we devised a method that casts regression as a conditional sequence modeling problem. This can, in some cases, match or even surpass the performance in predicting continuous properties, despite using a cross-entropy loss. And it's sort of like extending the benefits of self-supervised pre-training to numerically labeled data. The model is dichotomous because it can at the same time be used for conditional text generation. And the use case we think are most interesting are really local chemical space exploration. But now you might ask, okay, did you use the model? Okay, there I see him raised hand. Yes, please.
Yeah. Before you move on, I just want to check, like, in low data setting, have you kind of have more concrete results about like how well does it perform compared to pre-training and just learning a regression head on top of a protein representation? And
yeah.
Yeah.
So in low data setting, I don't have a comparison to for regression particularly. The regression was something we were not interested in the first place. So for me, the model, the benefits of the model is more in the generation, because you can like provide a property constraint that is arbitrarily precise, right? With floating points, you can really go as precise as you want. And you have a lot of flexibility on adapting the sequence. I have a real use case where we show how this model can be useful that I wanted to show now in polymer discovery. But that again is and this is a really small data, like low data regime, but it's on the generative task, not on the predictive task.
Okay. On the generative and the conditioning task, have you tried saying, okay, I want a molecule where the QED is greater than a certain value or lower than a certain value? Because everything I've seen so far is kind of exact condition equal, kind of equal conditions.
I'm not super sure I understand the question. So you mean whether we verified that the real, like the computed, so the QEDs of the obtained molecules were identical to the
No. If the condition, because the way you show the conditions so far, they were given as QD and a value, right? So it's kind of an inequality kind of things.
Yeah.
And what I was wondering, if you try like QD greater than 0.5, QD less than.
Okay. So no, we didn't try that. We always only tried with exact values. so you could, I mean, of course, I've seen papers also that then have specific tokens for high QED, low QED, right? And clearly, if you discretize it in such a way, you, I know, in my opinion, you lose a bit the control, right? Because you cannot ask for specific values. So why should you discretize if you don't have to? But of course, on the other side, you have no guarantee whatsoever that the result you will get actually has exactly that value, right? So I think either way is fine. I mean, to me, there was an interest in just trying whether like studying whether transformers can really understand numbers with a precision that is similar to yeah, just like a property prediction model. Yeah. Okay, so the use case I wanted to show. So let's go back. So you might ask whether we used the model for any real discovery, and yes, we did. We have an example here on ring opening polymerization. This is a paper that was actually published, I think, last month in Nature Communications. So ring opening polymerization is really important. It enables the development of sort of like biodegradable or biocompatible polymers, which are important in drug delivery systems or to produce eco-friendly packaging materials. And our collaborators, they devised this chemical markdown language. I don't want to go into the details here, but it's a flexible graph-based representation of polymers that allows them to store historical data. And we were interested in sort of like two design tasks. One was to design new catalysts that then would be coupled with an existing monomer to facilitate the polymerization reaction. And the other one would be to sort of like generate a block copolymer from scratch, like in a more challenging setting. Now, in the first setting, we trained the regression transformer consuming 3 properties. So in general, you can put as many properties as you like. The most I ever did, I think, was 12. I wouldn't recommend to do like 100 because the sequences get super long, of course, right? But for 12, it was still working okay. In this case, this is yeah, molecular weight conversion, which is the yield basically, and the dispersity. And then we have 2 chemicals, the monomer and the catalyst. Now, we were interested in designing new catalysts, so we always masked on the catalyst. We never masked on the monomers. We generated around 2.5 million pairs that were unique. And then we had subject matter experts looking at around 500 of them. And then we experimentally verified 5 of them, which you can see at the bottom. 2 of them are hydrogen bond donors, and 3 of them are Bronsted bases. And we used the same polymerization reaction scheme for all of them that you can see here at the top. Now, in one of the 5 cases, we didn't have enough activation to facilitate the polymerization reaction. We were able to fix this with a co-catalyst, which then allowed us to better control the dispersity. But in all the other cases, so in the remaining 4 cases, we obtained really performance single component ROP catalysts, basically, that produced a high monomer conversion. In general, we were focused here on the catalysts because the catalysts are mostly the component that is really driving the yield, the conversion. And yeah, this was decided by our collaborators, basically. We also observed in general, like in high agreement here between the predicted and the experimentally measured properties of these reactions. But then we wanted to take it to the next level, and we wanted to generate a polymer from scratch. And instead of like generating a catalyst that then is paired to a monomer to basically then facilitate the polymerization reaction. So one thing to note here is that this is a first of its kind generative model, in the sense that all existing generative models for polymers, they are either only on homopolymers or on very simple copolymers, but not block copolymers with a large space of possible repeat units. So what we did here is we took this chemical markdown language I mentioned before, and we serialized it. We arrived at these sequences that look very sort of like cumbersome. It looks a bit like smiles, but there are many meta tokens. And then we only have one property, the PDI here. And we trained the model on really, really small data in this case. It was like 100 data points or so they had. This was really a low data regime. The other one, I think, for the catalyst was like maybe 600, 700, but this was even less. Then we generated 2,500 block and statistical copolymers. And we did an experimental validation of one of them, which is this polycarbonate. So we always fine-tune the model, right? I mean, we never start training from scratch apart from the very first experiment on QED, right? We always fine-tune, and this is why it can work in such a low data regime, by the way. So we validated this polycarbonate, and the result is, first of all, I mean, we have a high agreement between predicted PDI and achieved one. And the second one is essentially, the polymerisation was successful. So we obtained the polymer that we wanted to generate. You can see here there's an agreement between the RI and the UV, which is just basically showing that the end groups of the synthesized polymer are correct. So yeah, this was a first of its kind generative models, and this is, I think, interesting for in polymer discovery, especially. So yeah, now I move to the next topic, to multitasking. So this was already touched upon one of the questions before, right? So this is really a trend that we've been seeing lately. Started actually long before ChatGPT. We had this we've seen this T0 paper at ICLR like last year, where they show that if you can actually pack task instructions into the prompt of NLP models, and you can reach exceptional performance in natural language understanding and also in sentence completion. And the question we asked was, well, can we transfer prompted training to chemistry? And we built a model for that that actually will be presented at ICML this month, actually next week. And the main goal here was to extend prompted training to multi-domain, multitask language models. And the reason for that was that in chemistry, one of the main obstacles is a lack of a unified representation between natural language and chemical representations. With this model, we've shown that we can solve a wide range of tasks just by prompted training. These include text-to-text tasks, like, for example, the blue one here at the top. We have a reaction, like a reaction procedure described as a text paragraph, and we convert it to like a sequence of actions we have to do. But we can also do cross-domain tasks like text to molecule. So this is a text-based molecular design. You start from a text description, you get out the smiles, or molecule captioning, the other way around, right? Or also we can do molecule to molecule tasks like classic forward or backward reaction prediction. So for this, we used the T5 model. T5 is an encoder-decoder model. And initially, we wanted to have domain-specific encoders. So for molecules, we took the ChemT5 encoder. And for text, we just took the vanilla T5. We played a lot with freezing versus tuning them. But interestingly, we found that sharing weights across domains remarkably improves performance of the model when we benchmarked it against sort of like task-specific models. This is interesting because we could show that we don't really need to have any expensive pre-training on chemistry data, just pre-training on text data, because we just took the vanilla T5 weights and fine-tuned them, and we were still able to achieve good performance in smiles-based tasks. So not so much in the first two columns here, which are just molecule to molecule conversion. So there we are really falling a lot behind to the specialized models for forward or backward reaction prediction. But if one of the two input or output was text, then actually we were able to surpass specialized models. You can see this here in the molecule design task and also in the molecule captioning task. We surpassed these specialized models. Okay, so the interesting thing about this model is that it can really facilitate execution of full discovery workflows with a single model. So here we have a case study on rediscovering monuron, which is a commonly known herbicide, and we compare our model to ChatGPT and also to Galactica. So we start with a text description of a molecule that we want, and the model has to provide the smiles string. We see that Galactica doesn't provide the smiles, but it gives the correct name of the molecule that we want. ChatGPT gives the smiles. It's almost correct, but it adds a methyl group here that is incorrect. And our model gives the correct answer in this case. Then the next step is to basically ask the model to come up with an reaction route, right? A synthesis route. So we asked for that. And you can see the results in the second column. So here, Galactica really produced garbage. ChatGPT did produce a reaction, but it's one that is not very likely to succeed. So we assessed this with the molecular transformer from RxN, and it gives a very low confidence that this reaction will succeed. But our model gives the correct reaction, basically. Then the last step was to basically ask the model to come up with a stepwise execution protocol on how to perform this reaction. The input for this was, in this case, not the output from the previous step, like for the first two, but in this case, we went to the literature. We took reaction procedure that is describing this reaction, and we gave this as an input, asking for a stepwise execution protocol. And here, ChatGPT, I don't expect you to read this, it's completely unreadable, but ChatGPT and our model sort of like conceptually succeeded in this task, whereas Galactica really produced, like a nonsense output, essentially. So it was really like mixing basically the product into the first step of the protocol. So I think this is an interesting direction to look into further. Of course, we will see multimodal models that can really help us to fundamentally accelerate research tasks. With this, we are slowly like arriving at the end. I want to leave also some time for questions. I want to emphasize that all the models that I was showing so far, they're all available here in the Generative Toolkit for Scientific Discovery. So that's an open source Python library that we have been developing in the team in the last years. There's really an ecosystem and a set of command lines tools for, in general, generative models in science, a bit with a focus on small molecules. There's a paper on this that also just came out in Nature Computational Materials. You can, with a single command from the command line, you can train a generative model. You can also just run any of the existing models that we have deployed there. And you can also, once you trained and saved your models, you can upload them to the model hub. It works a bit similar to the Hugging Face model hub. And at the moment, I think we have more than 25 different algorithms implemented there. There are many packages that we support that you can see here on the right. So we have GFlow nets, for example. I think there was a talk about GFlow nets last week, right? So that's included in GT4SD. There's also support for diffusers and transformers. So all the Hugging Face models are there. We also have more specialized libraries like TorchDrug, for example, and also more older ones like Guacamole and Basis. We have support for very important models like Molar, for example, which was at ICLR last year, so work from Microsoft. And as you can see on the on the left side, the library has a very modular structure, and there's a very harmonized interface to run any generative model with a few lines of code. Here I just want to emphasize the library also has property predictors for small molecules, for proteins, and for crystal structures. In general, we have these 6 high-level components. There are training pipelines, the algorithms, the command line interface, and the property predictors I was just mentioning. And then we also have Jupyter or Colab notebooks where you can have a look at example discovery, sort of like workflows or use cases. Last thing here, we have deployed more than 20 of the models that are in GT4SD. Using Hugging Face Spaces apps. So all of these apps are built with Grad.io, which is really a fantastic tool. So I think it makes it super easy these days to deploy a model on Hugging Face Spaces. The regression transformer, for example, is there. There are, I think, more than 10 checkpoints of the model available for to run inference in the UI, basically. And there are also model cards, documentation, example, inferences, and so on. And yeah, with that, I'm almost at the conclusion. So in general here, just want to emphasize for our team, since around 4 years has been focusing on lending techniques from NLP and to treat chemistry as a language. This sort of like started with the chemical reaction modeling, and then we got more into sort of like really synthesis automation. So we have models to predict these stepwise execution protocols, either from like paragraphs of reaction procedures or just from reaction smiles. And then in the lab in Zurich, we also have an automated synthesis platform and yeah, completely autonomous robotic lab that essentially can be interfaced with this cloud-based portal, RxM for Chemistry, where we basically give free access to all of these models. So you cannot use the robot without having the access token, but the rest of the services are freely available. And yeah, with that, I would like to thank you for your attention and for taking the time today to listen to the talk. Obviously, I mean, this is the most important slide because I have to thank a lot of fantastic people around me, without whom none of these works would be possible. So Dimitrios and Giorgio for really spearheading the text and ChemT5 work on multitasking, Matteo for being an incredible PhD advisor for me and co-authoring on all of these papers, Nathan for the polymer paper, and yeah, Theo for just being a very incredible leader, and then the rest of the team at IBM Research. So yeah, thanks to you, and now I'm happy to answer some more questions.
Perfect. Thank you so much for the great talk. If you have any question, please just raise your hand and come off mute to ask. I think there's a few questions in the chat maybe that you haven't answered yet. Guess I'll do those.
Okay, I see one about hardware. So what kind of hardware did you use? We used a single GPU training. It was, I think, NVIDIA A100. And yeah, model had around 100 million parameters. And we trained it for a few days. As I was saying, the training with XLNet is slow. So, but once the model got trained on the QED data, it really took a long time because this was a data set in the range of like a few millions. And then from that point, we always did fine tuning. So even when we started training the protein language models, we started from the QED, so from the small molecule model, and we just substituted the vocab. So you can train it with one line of code via GT4SD. If you do that, I always recommend to do fine tuning. Wondering if you try to combine a normal regression objective and the standard masked language modeling loss, for example. Yeah, okay. Okay, so yes, so the main problem I see here is I think with the gradient propagation. So sure, we could add like a regression hat on top. We didn't try that. We have comparisons for one of the experiments where we substituted in the output layer. Essentially, we plugged in a regression hat that is shown. 1 second. Right here. So this line here, RT with an XLNet backbone. So this is just a normal regression objective. And we can see that the performance is better. But we didn't try to combine this with the objective that we had. That was cross-entropy based on the tokens, mostly because we wanted to arrive at the model that is as flexible as possible and doesn't like depend on an additional hat. But it's an interesting idea. We definitely could have done it. Yeah.
I have one question about the data set for reaction protocol. Do you mind maybe sharing the more detail about that?
About the reaction modeling?
The reaction protocol. I think there was the one of the last slides when we were kind of asking the model to predict a protocol. You have three tasks.
Yeah. Let's go to the slide.
Yeah, this one. No, we just
This one.
yes, the last column. Yeah, I was just wondering how you train the model to be able to output the protocol line.
Yeah. So for this, let's have a look at another slide, because in the other slide, I have the references for the papers where you can find the details. And it is this one here, right? So essentially, we started with these reaction procedures that are, so some of them are in USPTO, so they're public. And then there's also data in Pistachio. So Pistachio data set is larger. Is also, because I also see the question in the chat now, is also public, but okay, I mean, okay, no, it's not public. I mean, you have to pay, but then you can get it, right? And the data set this was consisting of was really these paragraphs that were taken from patent literature. What then we did sort of like manually is to create this data set to train a model on paragraph to actions. So what we did manually in the team is that we would translate these protocols into these stepwise execution protocols where we have steps like concentrate, add, steer, and so on and so forth. And then once we had this data set that I think at least the small version of this is public. So once we had this data, then we were training this model. But I recommend to check out this paper here from my colleague Alan. Yeah.
Okay, perfect. Thank you.
Mm.
I think we can take one last question from Xingyu. Could you explain more about the problem with the numerical encoding? You mentioned the model somehow cheat.
Okay, let's have a look at the slide. So in general, the numerical encodings are not really necessary for the model to succeed. This is one of the things we realized. It was intended as a way, as an inductive bias, to make it easier for the model to understand that 6 is in between of a 5 and a 7, for example, right? And this is why we devised these embeddings that are governed by this equation here. But in the actual experiments here, and also in all of the other ones, but in this ablation study here, I think is particularly clear. We see a small benefit in having this embeddings, and they're not very costly to produce. This is why I would recommend to keep them. But I think if you are able to train the model a bit longer, then the model can figure it out by itself, right? I mean, I think this classical trade-off. Inductive biases are useful if you don't have enough data. And now we are using transformers a lot, and they have very few inductive biases, right, compared to the architectures we were using in the past. But it's not so much of a problem because we have enough data and enough compute to make it work. And it's a bit of the same stories here is happening here. So it's not a way for the model to cheat, right? It's just if the model has these embeddings available, it doesn't have to learn from scratch the ordering and the ranking of numbers.